Welcome to the acid-base equilibrium screencast number 3. Some acids, like sulfuric acid and carbonic acid, are what we call diprotic acids. They have two hydrogens that can be dissociated from the molecule. In general, acids that have more than one hydrogen ion that can dissociate are called polyprotic acids, and here are a number of the more common polyprotic acids: carbonic acid, hydrogen sulfide, oxalic acid, etc. Note that most of them are diprotic. They have two hydrogens that can dissociate, and we can often see this from the formula where it says H2 and then something else. And then here we have phosphoric acid, which is a triprotic acid, H3PO4. Polyprotic acids have a first dissociation constant, Ka1, a second dissociation constant, Ka2. If they're diprotic, that's it. And then triprotic acids also have a third dissociation constant, Ka3. Notice that there's a pretty big range of the size of the dissociation constants, Ka1, Ka2, etc. But the first dissociation constant is always bigger or a lot bigger than the second dissociation constant, which in turn is bigger than the third, if there is a third. As an example, sulfuric acid, H2SO4, is a diprotic acid, and back in Chem 1A, we might have talked about it as dissociating into two H plus ions and one SO4 2 minus ion, and it's a strong acid because it fully dissociates. Well, actually, only one of the hydrogen ions is fully dissociated from the molecule. So H2SO4 undergoes a complete dissociation into H plus and HSO4 minus, but there's a second hydrogen from the HSO4 minus that can also dissociate, and that is only a partial dissociation. So HSO4 minus has a double arrow to make H plus and SO4 2 minus. Now, in reality, all of the dissociations kind of happen very, very quickly, but we often think of it in terms of first dissociation followed by second, just to be able to track what's going on relatively easily. So, as a further example, how would we calculate the pH of a 0.1 molar, let's say, sulfuric acid solution? And to do this, we need to know the K sub A 1 and 2 of sulfuric acid, and then deal with the K sub A1 and K sub A2 expressions for sulfuric acid. So the first dissociation produces H plus and HSO4 minus, and that is a very large K sub A, lots of products, or pretty much full dissociation into quote-unquote products, and then essentially no H2SO4 left, so the ratio is a really, really big number, dividing by 0 more or less. The second dissociation is not as big a number for the K sub A2 ratio, but it is the same form, H plus times SO4 2 minus, which dissociated from the HSO4 minus. And what we're going to do now is essentially treat the first dissociation, figure out what's going on, and then from the results of that, move on to the second dissociation and analyze that, and eventually that'll give us the pH of the overall H2SO4 solution. So the first reaction is the one we saw before, full dissociation of H2SO4, and we'll set up an ice table here, but you could really just sort of think your way through this. Initially, we pretend there's no dissociation, so we have 0.1 molar H2SO4. Then we assume we allow it to change and dissociate, so plus X and minus X. And then at equilibrium, that leaves us with 0.1 minus X for H2SO4 and X for H plus and HSO4 minus. But since the first dissociation is strong, since K sub A is a very large number for the first dissociation, essentially what that means is to make this ratio very large, or the reason this ratio is very large is because we fully form H plus and HSO4 minus and essentially no H2SO4 left, so we get 0.1 molar H plus, 0.1 molar HSO4 minus, and 0 H2SO4. Now these we'll use for the starting concentrations when we do the second dissociation. So the second reaction is HSO4 undergoing a further dissociation to make H plus and SO4 2 minus. Initially, we have 0.1 molar HSO4 minus and 0.1 molar H plus, and we will say we haven't let it dissociate yet, so 0 SO4 2 minus. So these are essentially the results from the first dissociation. Minus X and plus X as appropriate. At equilibrium for the second dissociation, we have 0.1 minus X molar for HSO4 minus, 0.1 plus X molar for H plus, and X for SO4 2 minus. The second dissociation, K sub A, is 1.2 times 10 to the minus second. That's a ratio of H plus times SO4 2 minus divided by HSO4 minus. That equals 1.2 times 10 to the minus second. And now when we substitute in our X values, we get the equation shown, 1.2 times 10 to the minus second equals 0.1 plus X times X divided by 0.1 minus X. And solving in the usual manner gives us X equals 0.00984, carrying one extra sig fig on an intermediate calculation. Now note that X represents the SO4 2 minus concentration. It also represents the additional amount of H plus from the after the first dissociation to make H plus. And so what we have for our finding pH is 0.1 plus X. That's our H plus. That works out to be what we want to take the negative log of to get pH. So we're taking the negative log of 0.1 plus 0.00984. That's basically the negative log of 0.11, and that's 0.96. And notice this is a little lower than the pH we'd expect if there was just a monoprotic acid of 0.1 molar undergoing a complete dissociation. So the second dissociation gives us a little more H plus and a lower pH. Now, one other thing to note on this screencast, changing topics somewhat, this is something we saw in class. We often talk about an acid and a base reacting to make a salt, and we talk about it being a neutralization reaction. But of course, the salt that is made may or may not be neutral. Aluminum nitrate is very acidic. Sodium acetate is fairly basic. Sodium chloride is pretty neutral. So when we have an acid-base reaction, we might get a neutral solution, but we might end up with a salt that's acidic. We might end up with a salt that's basic. So what's going on here? Well, let's take a couple examples. First of all, KCl. KCl, the salt, dissociates into K plus and Cl minus ions in aqueous solution. And the K plus, it turns out, pretty much doesn't have an acid-base effect. And so we're going to ignore that for now. It's a spectator ion for acid-base purposes. And we'll come back to what positive ions might have an acid-base effect in just a bit. Cl minus, however, is the conjugate base of HCl, and so you'd say, well, maybe this could have a basic effect on the solution. But the thing is that HCl is a very strong acid, and very strong acids dissociate fully. Therefore, they give up the hydrogen ion very well. The Cl minus conjugate base does not accept a hydrogen ion very well. So if the acid's very strong, the conjugate base is so weak that it essentially has no acid-base effect. And so KCl is going to end up being an overall neutral salt because neither the K plus or the Cl nor the Cl minus have much of an acid-base effect. Okay, well, that wasn't super interesting. Nothing really happened, as it turned out. So let's try a different salt, sodium fluoride. Once again, it dissociates into sodium ions and fluoride ions. Sodium ion, it turns out, doesn't have an acid-base effect to speak of, or at least not enough for us to worry about for now. So that's a spectator ion, and we'll ignore it. Fluoride, however, is the conjugate base of hydrofluoric acid, HF, and so you'd say, well, maybe that could have a basic effect on solution. because it's the conjugate base of this acid. And what's different about HF by comparison to HCl is that HF is a weak acid. I mean, it's not the weakest acid out there, but it's somewhat weak. And if it's sort of weak, that means its base is not completely weak. So if we have a sort of weak acid, then the base has at least a little strength to it. And so F minus is going to have some basic effect on the solution. And if you think back to what we've done before with things like F minus, how it has a basic effect, F minus can react with water, pull an H plus off of the water to make HF, the weak acid, hydrofluoric acid, and when it does that, it leaves behind an OH minus, therefore basic solution, OH minus in it. So NaF is a basic salt because it contains a conjugate base of a not completely strong acid. And this is going to be true in general. Anytime we have a conjugate base of a not really strong acid, then the base has some basic effect, and it's going to give you a basic salt, providing the positive ion doesn't have a counteracting acidic effect. And that's the last thing we'll see here is an example of a positive ion that has an acidic effect. So iron nitrate in aqueous solution dissociates into Fe3 plus and NO3 minus, and NO3 minus is the conjugate base of HNO3, nitric acid. Nitric acid is a very strong acid, therefore nitrate ion is a very weak base, so it's going to turn out that the nitrate's not going to have a basic effect. But Fe3 plus does have an acidic effect. And why is this? Because we just talked about Na plus and K plus as not having an acidic effect. So here's a summary of why we can ignore NO3 minus as a base. It's the conjugate base of HNO3. HNO3 is a very strong acid, so NO3 minus is a really, really bad base, not going to accept hydrogen ion at all, so no acid-base effect from that. But iron nitrate is an acidic salt, so it's got to be coming from the Fe3 plus. So what's going on there? Okay, NO3 is an acidic salt. And what's going on there we'll demonstrate by example of something very similar. Aluminum is a +3 ion, and in aqueous solution, it gets surrounded by water molecules, and it looks like this. Here's an Al3 plus, and then it gets surrounded by 1, 2, 3, 4, 5, 6 water molecules. Highly charged small positive ion has the negative end of the polar water molecule attracted to it, and so we have a hexa-aqua aluminum 3 complex ion. And then furthermore, because the aluminum ion has such a big charge, it actually withdraws or pulls some electron density from the water molecules. And it does that enough, if it pulls electron density enough towards itself from the water molecules, that at least sometimes, once in a while, one of the OH bonds in a water molecule that's attached to the aluminum ion, once in a while one of those bonds breaks, and when it does, an H plus comes off of it, it dissociates, and then that can stick onto a nearby water molecule. So what ends up happening is the AlH2O6 with a +3 charge near water can form AlH2O5, so 5 of the water molecules, this one, this one, this one, this one, and that one, are left intact, and this water molecule right here loses its H plus and leaves behind an OH, so all but the H part of the 6th water molecule. So it's H2O5, 5 intact water molecules, 1 OH. Since it's lost an H plus, the charge goes down by 1, and then it produces H3O plus, thereby making an acidic solution. And this is going to be, in general, what happens if we have a small, highly charged cation, positive ion. It's going to have an acidic solution an acidic effect on aqueous solution by weakening the OH bond in a water molecule, allowing transfer of a hydrogen ion.